next maybe. Just wait a minute.
Yeah, we can start, sir. Screen visible, sir.
Oh, screen is visible. Has everyone come? Can I start? No.
1 minute, sir. Let me check, sir. Prem, how many people are sitting in MTA? Right now, I'm not there. That is why. Hello?
Yeah, we can get started.
Okay.
Then we'll see. So let's continue. So previously, if you recollect, we were looking at the Bode plot, and in the last class we looked at the Bode plot of can you really mute the microphone? Please. Arnav sir, can you mute your microphone if you don't know? Yeah, all right. Okay. So we were looking at the second order factor, which is what's the omega n squared by s squared plus 2 zeta omega n s plus omega n squared. And then we saw what the behavior of the second order factor was as far as the Bode diagram is concerned. And then we identified that the resonant frequency is the frequency at which the magnitude of the corresponding sinusoidal transfer function becomes a maximum. So that's omega r. And essentially, we saw that this is meaningful only when zeta is between 0 and
one important advantage in classical
magnitude expression
is that we can
we observe that
the methods that are associated with complex algebra. We can
family of
process
right? So
the
as far as
system equation, the complex domain,
where
where bodies become algebraic equations, and then we use inverse plus to come back to the
high frequency asymptote is straight line at the slope of minus 40 degrees per decade. And
so if we look at control system design,
characteristics of the essentially the Bode plot of this. I left you with exercises.
And we are looking at a closed loop system.
The expression for omega r,
these two things become
we'll be able to get expressions for the
stability and then
value, right, of the magnitude at the resonant frequency and the phase of the resonant frequency, and also the Bode plot of the reciprocal. Okay, so that's where we stopped in the last class. Okay, so let's continue from there today. Once again, as we learned, of course, one can just use this command called Bode in MATLAB Simulink and just directly generate the Bode plot. Okay, in MATLAB, but as I told, the reason why you and I are learning the Bode plot in this manner, in this detailed manner, is to ensure that we have we have a clear understanding, right? Of the fundamental concepts behind the Bode plot, and we also have are able to figure out the transfer function of a system from experimental data. So using experimental data, you and I can observe and then interpret the transfer function from the Bode plot. And a couple of important points in that regard is that we use these two factors to our advantage when we also do experimental determination of the transfer function. So let us say as we know, the plant transfer function is a ratio of two polynomials, n of s and c of s. Now, n of s is a numerator polynomial of order m, and the numerator denominator polynomial d of s is a polynomial of order small n. And to begin with, let's assume that all poles and zeros are in the left of complex plane. So if that is the case, it can be shown, right? We are once again using the result. Can be shown that the high frequency asymptote, right, of the log magnitude plot of the Bode plot has a slope of minus 20 times n minus 1 decibels per decade, okay, as omega keeps on increasing. So if some Bode plot, right, we obtained from essentially experiments has a high frequency asymptote of minus 60 decibels per decade, right? If you and I equate it to minus 20 times n minus m, we will get the n minus m to be 3. Okay, so this is pretty useful when we want to sort of like like reverse engineer the plant transfer function for the Bode plot, because this is what is called as the relative degree of the plant transfer function. It is essentially the difference between the degree of the denominator polynomial and the degree of the numerator polynomial. That is one fact, okay, which we will be using later on, okay, when you do the project. So then we also have another interesting fact wherein if you have a minimum phase system, okay, so if you recall what was the minimum phase system, that means all zeros should be in the left of complex. Okay, so if that is the case, then the phase of the plant transfer function tends to minus 90 degrees times n minus m as omega tends to infinity. Okay, so that is why it is called as a minimum phase system. Okay, so the phase becomes the minimum only when all the what to say zeros are lying in the left of complex. Okay, so that is an important also result. Okay, so in essence, if we if from a log magnitude plot, if we determine the value of n minus m to be 3, what do you think should be the asymptotic value of the phase plot if the system were a minimum phase system? From this result, so if n minus m is 3 from the log magnitude plot, if all the zeros lie in the left of complex plane, what should be the final value of P of j omega as per this formula?
Minus 270 degrees.
It should be minus 270 degree if the system were minimum phase. So from the Bode phase plot, we can look at the phase. Okay, if the high frequency phase angle is tending towards minus 270 degrees, then you and I know that it's a minimum phase system. That is, all the zeros are in the left of complex. But if it tends to some other value, then we know that there are zeros in the right of complex. So you can see how we can use these results to our advantage as we go forward. However, please note that the slope of the log magnitude plot will always tend to minus 20 times n minus m decibels per decade, irrespective of whether there are zeros in the right of plane or the left of plane. We need all the poles to be in the left of complex. Even this analysis is meaningful in the first place. So the slope of the magnitude plot will be always minus 20 times n minus m decibels per decade for both minimum phase and non-minimum phase. Whereas only for a minimum phase system, the phase will tend to minus 90 degrees times n. Okay, so these are two important results, okay, which help us figure out the transfer function of a system from its Bode, right? Okay. So now let's do an example. Okay, so let's consider a plant transfer function s plus 1 by s plus 10. You and I can immediately observe that the value of n is 1, value of m is 1. There is a 0 at minus 1, the pole at minus 10. Okay, so now we are asked to construct the Bode plot of that. Okay, so we need to put it in the standard form. Please note that it's not yet in the standard form because we need ts plus 1 and 1 by ts plus 1. That means the constant term should be 1. The constant term is 1 in the numerator, but in the denominator, the constant term is 10. So what do? We do this. Okay, so we pull 10 out of the denominator we get 10 times s by 10 plus 1. So if we take 10 to the numerator, it becomes 0.1. And then like this becomes 0.1 s plus 1. Okay, so that's what we have. So in essence, we have three terms. Okay, the first term is 0.1. The second term is s plus 1. And the third term is 1 by 0.1 s plus 1. Okay, so we plot the magnitude plot of the three plots, add them. We plot the phase plot of the three plots and then add them. Okay, that's what we are going to do. All right. So I hope this till here it's clear. Okay. So now please help me with the calculations. Okay. So already the calculations are before us. You know, like it's going to be we are just going to recap that, right? So let's say the first factor is 0.1. If I take the magnitude of 0.1, it's a constant, right? So we take 20 log of 0.1 decibels. A log of 0.1 is minus 1. So we get the magnitude to be minus 20. So please note that the magnitude of, you know, like the, what to say, 0.1 factor is always going to be, you know, like minus 20. Okay, so that's what we will have, right? So then, you know, like if we look at the phase, it is going to be 0. Why do you think the phase of 0.1 is 0?
Because there is no imaginary part associated with this.
There is no imaginary part, and importantly, where
It is on positive real.
it lies on the positive real axis, right? So consequently, what happens is that like the phase is going to be 0 degrees, right? When we have this one, right? So that is the bottom line, all right? Okay. So now, if we go to the factor s plus 1, s plus 1 is like that factor ts plus 1, right? So what will be the corner frequency? It's 1 by t, right? So for s plus 1, what is the value of capital T?
1.
1, right? So what is 1 by t? It is also 1, right? So that's why the corner frequency will be 1 radians per second. And high frequency asymptote has a slope of 20 decibels per decade. Okay, so that's what we have for s plus 1. Okay. Now, if we similarly go to 1 by 0.1 s plus 1, what is the value of t here?
0.1.
0.1. So 1 by t will become
10.
10. Okay, so that is why this has a corner frequency of 10 radians per second. Okay, so and once again the high frequency asymptote will have a slope of minus 20 decibels per decade. Right? I hope these points are clear. Okay, so now with this understanding, what we do is that like we go ahead and you know, like plot all the individual variables. Okay, so let's say we first start with you know, like the magnitude plot. What happens is that like if you essentially you know, like start plotting the individual plots, the first plot is for 0.1, right? I have plotted it using a blue dashed line. So what is the magnitude of 0.1 in decibels?
Minus 20 dB.
Minus 20 decibels per decade. Sorry, minus 20 decibels, sorry, right? That is why you can see that the blue line is constant at minus 20. Okay, so you can see the blue dashed line. And how did I choose this frequency range to plot? See, typically what we do is that like you and I, we choose a frequency range which is 1 decade above and below, right? The frequency of interest. Okay, so what do I mean by that? What are the two corner frequencies? Two corner frequencies are
1 and 10.
1 and 10. So this is the range. So I choose, we have to choose one typical, it's a rule of thumb. Okay, once again, nothing is set in stone. But the rule of thumb is that like we choose 1 decade above the below the lowest frequency and 1 decade above the highest frequency, right? So what is 1 decade below the lowest frequency?
0.1.
0.1, right? And what is 1 decade above the highest frequency?
100. 10.
10. Sorry, above 10, right?
100.
100.
Yeah.
Right? So that's what you and I choose, right? And essentially we essentially go from there, right? Consequently we choose this what to say, frequency range. So and then start plotting. So the first thing is that, like, for point one, it's just at minus 20 decibels, so it's a flat line. Then we take TS S plus 1, which is this green line. So once again we plot only the asymptotes. The low frequency asymptote of S plus 1 is the 0 decibel line, right? So we plot 0 decibels till the corner frequency of 1. And then, like, we draw a line with 20 decibels per decade slope above the corner frequency. How do I measure 20 decibels? Because at 1, how do I measure slope of 20 decibels per decade? If at 1, if it's 0 decibels, at 10 it should be plus 20 decibels, right? That is when I'll have the slope to be 20 decibels per decade. So I draw a straight line passing through both these points, right? That is the green dash, right? I hope it's clear how we got for S plus 1. So we have done 0.1 and then we have done S plus 1. Now, similarly, how do we do 1 by 0.10 S plus 1? That is the magenta line here. So the corner frequency is now 10. Then the low frequency asymptote is the 0 decibel line. Then the high frequency asymptote is minus 20 decibels per decade slope, right? So how do I plot the minus 20 decibels per decade? At 10, I have 0 decibels. At 100, which is 1 decade above, I have the value to be minus 20. So essentially, I draw the line which passes through 0 and minus 20. And that is the high frequency asymptote of 1 by 0.1 S plus 1. Okay. And that has a slope of minus 20 decibels per decade. All right. So these are the three individual graphs. Now, what do we need to do? I hope this is clear, right? How we got these three individual graphs. Okay. Yeah. So once we get these three individual graphs, what do we need to do? We need to add them, right? The question is, how do we add them, right? So how should we add them?
It should be logarithmic addition, sir.
So we just need to keep starting from low. Is going to be the resultant value of the three factors. Please note, S plus 1 and 1 by 0.1 S plus 1 will be 0, right? Correct? Whereas 0.1 has a value of minus 20, right? So that is why this red line, which is the resultant curve, has a value of minus 20 till the corner frequency of 1. I hope that is clear, right? Okay. So then, the factor S plus 1 kicks in, right? So above the corner frequency of 1, when the factor S plus 1 kicks in, what do you think will happen? S plus 1 has a high frequency asymptote of 20 decibels per decade here, right? So what will happen? From minus 20, we will start increasing because we have plus 20 decibels per decade till I reach the second corner frequency of 10, at which point the value will become 0. Why do you think the value becomes 0? No.
Because for 1 decade, it will be 20 dB.
Exactly. See, at the frequency of 1, I start from minus 20. But then, however, the slope of the high frequency asymptote is plus 20 decibels per decade, right? When I go from 1 to 10, the value will increase by 20 decibels, right? So the value goes from minus 20 decibels to 0 decibels, right? I hope it's clear, right? How we got that. All right. So that is the second factor. Now after that, the factor 1 by 0.1 S plus 1 kicks in. Now when 1 by 0.1 S plus 1 kicks in, what do you think will happen to the total magnitude plot? Why do you think this is becoming a flat line?
Because
They will cancel each other.
cancel each other. Yes.
Exactly, right? S plus 1 has a high frequency asymptote of plus 20 decibels per decade, whereas 1 by 0.1 S plus 1 has a high frequency asymptote of minus 20 decibels per decade, like, so the sum is going to be 0 decibels per decade, right? So that is why it is cancelled, okay? So it becomes a flat line, all right? So I hope that is clear, right? So essentially this red curve becomes the resultant, like log magnitude curve of P of G. Okay, so that's what you and I get. All right. So I hope it's clear how we get the resultant curve. Okay. Any questions on this? Okay. So this is how we plot the a log magnitude plot. That is, like, what we do is that, like, we essentially have the what to say, individual factors. We plot them, and then, like, what we do is that, like, we just add them, right, to get the resultant log magnitude plot. Okay, so that's what we do. All right. So then the phase plot. Okay. So the same story, right? What do? We essentially plot the phase plot by adding the 3 phases, right? So what is the phase of 0.1? Yes, please.
Sorry to interrupt here because we were trying to unmute, but it was not working. Can you slightly go up?
Yes, please.
Sir, one query on why it is actually remaining at -20 till 1.
Till 1, because there are 3 factors, right? See, 0.1, S plus 1, and 1 by 0.10 S plus 1, right? So at low frequencies, this will always give -20 decibels, right? This will give 0 decibels. This will give 0 decibels, right? So where will it start?
Okay. Noted, sir. Noted.
Right? Yeah. So that is why this asymptote thing helps, right? I hope it's clear, right? So,
and just one other question. The one that is getting cancelled in the S plus 1 as well as 1 by TS plus 1, that is what we are essentially meaning as a low pass filter, right?
So see, this becomes sort of like like a relatively other shape. In fact, like this actually factor corresponds to what is called as a lead compensator. Okay, so this is not exactly a low pass filter, because you can see that relative to the low frequencies, the high frequencies are getting magnified. But we will see that this factor, in fact, provides positive phase to the system. That means we are going to realize it from the phase plot. So essentially what happens is that, like, when you have a positive phase, like, you see that, your system response, okay, becomes faster. Okay. So that's the point, right? So here it is not exactly a low pass filter, right? It is what is called as a lead compensator. Okay. So that is this one. Right.
Okay, sir. Yeah. Thank you.
Okay. Any other questions? No. So essentially, yeah. If we now come to the essentially phase plot, we once again plot the phase of the 3 individual factors and add them. Okay. So that is the phase plot. So as we know, the phase of 0.1 is always 0 degrees. The phase of S plus 1 goes from 0 to 90 degrees, okay, with 45 degrees at the corner frequency of 1. And the phase of 0.1 S plus 1 goes from 0 to -90 degrees. With a corner at the corner frequency of 10, the value becomes -45 degrees, right? So that's what it is. So if you add it, of course, this part, we may need to do some computations, right? Ultimately, like, the phase of P of J omega comes something like this. So if you look at it, this red curve is the phase curve. It will keep on increasing from 0, and then it will reach a peak, which happens to be the geometric mean of the 2 corner frequencies, and then it decreases. Okay, so that is a feature of what is called as a lead compensator. So to know more about this lead compensator, you can watch the videos on control systems. Okay, so in the last week I have discussed about the lead compensator. Okay, so please watch that. All right. So essentially, the reason I gave this example is because this is a very, what to say, interesting case. We can immediately observe, right, as I mentioned in my, what to say, response to Prem's question shortly before, that in this particular case, the phase is always positive, right, for all frequencies, okay? So it essentially results in what is called phase lead, okay? So phase lead means positive phase, okay, as a transfer function. And that's something which is very, what to say, good about this, right? Because a positive phase ensures better system response, okay? And faster system response, okay? So that is why, the lead compensator many times helps improve the transient response, okay? So that is one feature of a lead compensator, okay? So I hope it is clear how we got this lead compensator, how we got this particular transfer function, all right? And the Bode plot of this transfer function, okay? So any questions about this? So in this, I'm leaving it to you as once again an optional exercise to do. You don't need to submit it as a homework, but once again, you can, do it as a assignment or an optional exercise to find the frequency at which the phase will be maximum. So once again, the frequency at which the phase is maximum is the geometric mean of the two corner frequencies. Okay, the two corner frequencies are 1 and 10. So what do you think is the geometric mean?
It's basically, sir, root square of
Root 10.
number 1, number 2.
Under root 10.
So geometric mean of what to say, essentially the what to say, two numbers is the square root of the product of the two numbers, right? So that's what it is. So essentially what happens is that like we take the two corner frequencies 1 and 10, we multiply it, and then like we essentially get the what to say, the geometric mean. So in this case, it's square root of 10. And what is the value of square root of 10? What is square root of 10? If you do in the calculator,
3.16.
it is 3.16 radians per second. Okay, so that is the frequency at which you will get the maximum possible what to say, phase, right, addition through this particular transfer. Okay, so this is something which I leave it to you as an exercise to, right? Fine. Optional exercise, but this is a homework. I believe this is still homework 4, right? We have done 3 homeworks till now. Am I correct?
Yes, sir.
So kindly do this as the 4th homework. Okay. The 4th homework is this, where we have this plant transfer function. I want you to draw the Bode plot, right? As we discussed today. That is, plot the magnitude plot or the phase plot. You can essentially use the asymptotes, okay, to draw the plots, all right? Okay. So you can certainly draw using the asymptotes, and then like you can plot the total Bode plot. Okay. So how will we construct the Bode plot in the standard form for this particular factor? So S is a standard term.
We will take 3 factors: S plus 1, and S 1 divided by S plus 2.
Okay. Roshan, please note, it should be in the standard form, Ts plus 1 and 1 by Ts plus 1, right? So the constant term should be 1. Is the constant term 1 for all the factors?
No.
So what should I do?
So 10, we will take 10 out of the box, and
exactly.
0.1.
Right. So we will have 0.1 S divided by S plus 1 times 0.1 S plus 1. Am I correct?
Right, sir.
Yes.
So we'll have 4 factors: 0.1 S, 1 by S plus 1, and 1 by 0.1 S plus 1. So we know what is the Bode plot of 0.1. We know what is the Bode plot of S. We know what is the Bode plot of 1 by S plus 1. And we also know what is the Bode plot of 1 by 0.1 S plus So please plot the log magnitude plot of these 4 factors and then add them. Similarly, please plot the what to say, essentially the body, the face plot. Okay, then add that. Then you will get the total body plot. Okay, so essentially, we can do that. All right. Okay, fine. Okay. Any any questions on this? Hello.
Sir, do we need to submit this homework in midterm, during midterm?
Okay. So do you want to submit it this time or you want to submit it later?
So later
It is not a part of
better.
syllabus this time, so maybe next time.
Okay. So essentially, if you want to submit it, we can essentially submit it later also. Okay. Yeah. All right. So you submit homework 1 to 3 when you come here this particular Sunday, right? And then we can go ahead and submit homework 4 when you come for the end semester exam. Okay, with the remaining due homeworks. Is it okay? No, sir.
Yes, sir. Thank you.
Okay. Fine. So I think we will stop here for today. We will discuss Nyquist plot and the remaining concepts in related to frequency response tomorrow. With that, we will complete our discussion on classical control. But then we will also look at the state space representation starting from Wednesday. Okay, so that's what we will. All right. So any questions on what we discussed today, please?
Sir, we will revise. 1 second. Sorry about the echo. Yeah, sir, we will revise once and then we'll ask the question, sir.
No problem. Then I think what we can do is
audible?
Yes, Prem, you are audible. Yes.
Sir, am I audible?
Yes, Prem, you are audible.
No. I just wanted to say that we will revise once and ask the question, sir.
Okay. Understood. Okay. So what we can do is that we can then continue tomorrow. But I think Arnachalam, what is the status of attendance? Is everyone present?
Yeah, everyone present, sir.
Okay.
Sir, I want to ask one question from the previous topic, if possible.
Please go ahead. Please go ahead.
Sir, basically, while plotting that, just a minute, sir. Root locus, sir, basically. And we are trying to calculate what is the break-in and breakaway points. That is step number 4, if I'm not wrong.
Okay.
So basically, sir, if I solve that and put the value of s is equal to step number 6, where the points is crossing the locus is crossing the imaginary axis or not. In that case, we are putting the text s is equal to j omega in the characteristic equation and solving that. Sir.
Correct.
So at that time, if we get the value of k to be negative, that means we have to ignore that. Means what I mean to say is that means that is not a feasible thing actually.
For k greater than 0. See, there's a subtle point here, Roshan. That is, if we start with the assumption that our open loop transfer function is of the form k times s plus z1 all the way till s plus zn divided by s plus p1 all the way till s plus pn, and we take k to be a positive number. Okay, that is a premise with which you and I are starting. If we question that premise, we can always do from k to be minus infinity to plus infinity also. Doesn't matter. That is why you remember we wrote down the script, right? Finally, right? It's just that, like we can do only one thing at a time. Okay, that's how the theory is set up. That is, so if you come and tell me, hey, you know what, like I take the open loop transfer function g of s h of s to be k times s plus z1 all the way till s plus zn, right? Divided by s plus p1 all the way till s plus p1 pn, and I want to plot the root locus for all k going from minus infinity to plus infinity, right? So
Right.
let's say you adopt that as the question. Then what you need to do is that you need to solve two questions. First, you plot the root locus for k greater than 0, where you use this set of steps. Then in the same plot, you plot using the steps for k less than 0. You use this step, okay? So that's the broad picture answer. Okay, point number one. Roshan. The second point is that we essentially have the way things are set up in the breakaway point calculation and also the crossover point. We solve for potential roots and we check for k. The question is which case we are dealing with. So let's say if you and I are plotting the steps for k being positive, if the value of k happens to be positive at that value of omega or sb that you and I calculate, then that is either a crossover point or a breakaway point. Okay. If it's negative, it just means that for the first set of steps where you consider k to be positive, that is not a crossover point or a breakaway point. Okay,
Fine.
I hope that is
Got it, sir.
right? Yeah.
And the second query I have, sir, suppose if I have a polynomial like I'm spelling the equation, sir, basically it's s square plus 4s plus kp. For timing, I'm just telling you.
Okay.
So if we apply the Roth criteria over here, it's a second order polynomial, and the coefficient, all the coefficients are not non-zero. And secondly, the coefficient should be positive, all are positive. So if the system to be like stable, the kp should be more than 0. That's the thing we have learned, right, sir?
So the necessary and sufficient condition for polynomials till order 2 to be Goodwitz is that all coefficients must be non-zero and of the same sign. Okay. So
Right.
I am reiterating that, Roshan, because sometimes mistakes can happen. It is not positive, right, by default. Okay.
I got the point. Same sign. I'm sorry, sir. Same sign.
I'm just reiterating the point here, Roshan. It just happens that this happens to be +1, this happens to be +4. That is why kp should be greater than 0. Suppose if the polynomial were minus s squared minus 4s plus kp, then kp should be less than 0.
Negative.
Okay,
right, sir. So in this case,
still polynomials of order 2. Okay.
Right, sir. I got the point. So thank you for that, sir. The second point of the question is, sir, suppose if the system if system has to be stabilized or stable, then the roots of this equation, suppose s1 and s2 are two roots.
Okay.
If we find by minus b plus minus under root b square minus 4c divided by 2a, then that should also be negative, right, sir?
Roots b squared minus 4ac being positive or negative
No.
whether you're getting real roots or imaginary roots. Okay.
Sir, basically, I'm talking about like Roth criteria. I found out, suppose kp should be greater than 0 in this case particularly because the sign of the s square is 1, right, sir? Now, further to fine tune a kp, do I need to find the roots of this equation and then the imaginary root should be like what I mean to say is like it should be left plane. It should lie on the left plane of the S plane.
kp greater than 0 immediately means the two roots are going to be in the left of complex. Okay, that is guaranteed in this case, right? So what you are asking for is now whether the two roots are on the real axis or can I have complex conjugate roots. That's a different question to ask. For that, you need to ask b squared minus 4ac, right? Then b squared minus 4ac, it's 4 squared minus 4 kp, right? If you want imaginary roots, this should be less than 0 or kp should be greater than 4. If Kp is greater than 4, you will have complex conjugate roots. If Kp is less than 4, you will have roots on the imaginary axis. If Kp is exactly equal to 4, you will have repeating roots on the real axis. Okay,
Okay, sir. Okay, fine.
I hope
got
that
it.
is clear, right?
Yeah, it's fine.
So, yeah. So, because if Kp is 4, you will have s squared plus 4s plus 4. And that is essentially nothing but s plus 2 whole square, right? Is it not? Okay. So, you will have repeating roots on the negative real axis. Okay.
Thank you, sir. I got it, sir.
Okay.
Completely. Thank you, sir.
All right. Okay. I think Arunachan, you told everyone was present, right?
Everyone is present. In the MTA room, nearly 7 persons are sitting.
I didn't get you. I didn't get you.
Sir, in MTA room, in MTA, 7 people are sitting.
No problem. Like I just wanted reconfirmation that everyone is present. Right? Yeah.
Yes.
All right. Okay. Any other questions? Okay. So if not, maybe then we can meet tomorrow, right, at 5 p.m. and then like continue with our discussions. So I hope the preparations for the exam is also going on fine. You can also ask me questions regarding the exam, right? No, of course, questions related to the exam, not questions about it. Right? So, okay. So if you have any doubts, you can always ask, right? And don't worry, like I'm giving you 1.5 hours for the exam. I could solve it in 10 minutes. Okay, so you have a lot of time to solve the exam. Okay, so it's pretty straightforward. All right. And did we agree that you can bring a one-page sheet?
Sir, if you're solving in 10 minutes, we will require around 100 times multiplied with that.
No. I'm giving you 90 minutes. So I solved very, very slowly. Okay, and then.
Sir, there is another question from our side. Is it similar to VD paper?
I don't know, Prem. Like I think you can for yourself. Like, but I wouldn't be too worried about your batch. I think your batch overall is pretty good. Like you're doing well.
Sure, sir. It's just the topics are a little bit tricky, right? That's the reason why you wanted to know.
Yeah. So I think once again it's going to be pretty straightforward. No issues.
Noted, sir. Thank you.
So as agreed, you can bring one formula sheet, that is one side of a one A4 sheet. Okay, that is allowed.
Sure, sir.
And please bring your own calculators. No exchange of calculators. Yeah.
Sure, sir. Got it.
All right. Then
Thank you, sir. Thank you so much.
Thank you very much. Like I think we can then like meet. Okay. Bye bye.
Okay, sir. Thank you, sir.
Thank you, sir.